Welcome to the fifth and final part of Unit 10. In this part, we're going to work a couple of examples using the work energy theorem. So here is our first example. We have a 5 kilogram block sliding across a frictionless surface, and it has a kinetic energy of 50 joules. It then comes to a rough patch, and I give you the coefficient of friction being 0.5. If the block is still to be moving when it reaches the other side, how long can the rough patch be? The key to this problem is determining how long is the rough patch to just get the block to stop moving. And then we know that if it is just a smidge shorter, it would still be moving, if barely, when it reaches the other side. So as always, start off by drawing yourself a picture. So here's my block. It's got its velocity this way with 50 joules of kinetic energy. It's a 5 kilogram block. And over here is our rough patch. And that rough patch has a length of d and a coefficient of kinetic friction of 0.5. Okay, so looking at the free body diagram of the block, when it is in the rough patch, you have the normal force up, you have weight down, and you have friction pointing to the left since the block is moving to the right. We can then use Newton's second law in our two directions. So in the vertical direction, there's no net force, so the net force in the y direction is 0. Which tells us that our normal force equals the weight force, which equals mg, which is 5 kilograms times 9.8 meters per second squared, which is 49 newtons. We can then find the force of friction by saying friction is fun, UK times NSB, which is 0.5 times 49 newtons, which is 24.5 newtons. And that's not a very good force, so there, that's a little bit better. I now have all the information I need to use the work energy theorem. So the work energy theorem tells me that the work is FD cosine theta, but it also equals the change in energy. And what I want to know here is D. The force that matters is the frictional force, D cosine. The angle in this case will be 180 degrees because the velocity is this way, friction is the other way, and that is 180 degrees. Energy is only kinetic in this case, so final kinetic energy minus initial kinetic energy. Now, remember, the idea here is find out how long that rough patch can be so that it just loses all of its energy. So that makes our final kinetic energy equal to 0. The initial kinetic energy was 50 joules. Friction was 24.5 newtons. D is what we want to know, and cosine of 180 is a negative 1, so I can put a negative sign out front. 0 minus 50 is 50, so the distance will be 50 joules divided by 24.5 newtons, which equals 2.04 meters. So the answer to this question is if D is less than 2.04 meters, then the block, that B did not work very good. Let's try again. The block will still be moving on the other side. Okay, that concludes this example. We're going to move on to the next example, which involves a falling raindrop. So A raindrop has a mass of about 10 to the minus 6 kilograms, and it falls from a height of about 3,000 meters. Those numbers are fairly reasonable for the mass of a raindrop and the height it falls from. It reaches a speed of 10 meters per second before it hits the ground. And we want to know how much work does air resistance do on the raindrop as it falls, and what is the average force on the raindrop. So again, drawing a picture is always a good place to start. So up here we have a cloud, and in that cloud is a raindrop, which is going to have an initial kinetic energy of 0 because we can assume it is at rest up there. But it has an initial gravitational potential energy given by mgh, where h is the height of the cloud above the ground. In other words, 3,000 meters. The raindrop then falls, and right before it hits the ground, its energy is strictly kinetic, and its gravitational potential energy is 0. So this guy's now moving downward. Okay, so first thing we want to know is how much work is done. Well, work equals the change in energy, which is going to be E final minus E initial. Our final energy is strictly kinetic. Our initial energy is strictly gravitational. So 1/2 mv final squared minus the gravitational potential energy, which is mgh initial. So 1/2 times 10 to the minus 6 kilograms times 10 meters per second squared minus 10 to the minus 6 kilograms times 9.8 meters per second squared times 3,000 meters. And if you put that all in, that gives a negative 0.02935 joules. So there is roughly negative 0.03 joules of energy removed from this raindrop as it falls, and the force that is removing the energy is air resistance. So that answers the first part of this question. The next part of this question was, how big is the air resistance force? Okay, so now we got to think about forces. So I have air resistance upward and the gravitational force downward. Remember, the gravitational force is mg, so that's 10 to the minus 6 kilograms times 9.8 meters per second squared, or in other words, 9.8 times 10 to the minus 6 newtons. Now I can take the other definition of work and use it to get a handle on how big the force is on average. And the reason it's a force on average is because as the raindrop falls, that force is going to change its value. And this analysis is not letting us pick up on how that is changing. So all we get is a kind of smear look at it, an average. We know from the previous slide that the work was 0.02935 joules, and I'm keeping a lot more digits here than I normally would. The force in this case is what we want to know. So force of the air on the drop. D is going to be 3,000 meters because that's the distance it falls through. And our angle is going to be 180 degrees because friction points upward and velocity points downward. And if you put that all in, you get that this force is 9.783 times 10 to the minus 6 newtons. Okay. Which is really close if you look to what the weight of the drop is. Which means, because the force here is roughly equal to the block's weight, that this drop, I said block here a minute ago, I meant drop. The drop is reaching terminal velocity. Okay. So, as one more piece to this puzzle, let's see how fast the drop would be moving if there was no air resistance. So in this analysis now, we got up here 3,000 meters up. Here's our pretty little drop. Again, we have only gravitational potential energy to begin with. Kinetic energy is 0. This is our 3,000 meters. And down here, we're going to be moving downward at a velocity. So kinetic energy will be 1/2 mv squared. And in this case, the only force acting on this drop is gravity. And because gravity is one of our conservative forces, we don't need to worry about the work because it's taken care of by the potential energy piece of it. Okay, so work equals 0 because no air resistance. So that means our change in energy has to equal 0. So GPE, oh, I wrote that, yes, I wrote that backwards. And I have an I up here that really should be an F. Okay, so KE final minus GPE initial has to equal 0, which means 1/2 mv final squared has to equal mgh. The m's cancel. And we get v final equals the square root of 2gh. And if you put that all in, you will find that without air resistance, when that raindrop comes down right before it hits the ground, it would be traveling at 242.5 meters per second. And I don't think any of us want to be hit by a raindrop that is moving that quickly. Okay. Our last example. Here we have a question about braking distance. So if the speed of a car is increased by 50%, what factor will its minimum braking distance be increased, assuming all else is the same? And we're going to ignore reaction time. Okay, the first thing I want to do is get an idea of a formula for braking distance. So we're gonna start there, and then we're gonna worry about this whole speed increasing by 50% thing second. So what do I have? I have a car happily moving at a speed v. And sometime later, or some distance later, it is no longer moving. And here is the distance we want to find. We have an initial kinetic energy. Our final kinetic energy is 0. So going to our work energy theorem, the work is going to be FD cosine of theta equals our change in energy, which is E final minus E initial. Now, the force that is causing this car to brake, if you think about it, we have normal of the road on the car, we have the weight of the earth on the car, and then we have friction between the road and the car. So friction is again the force that is going to cause our change in energy and provide our work. So that's FRC times d, and that angle will be 180 because velocity is to the right, friction is to the left. Our final kinetic energy is 0. Our initial kinetic energy will be 1/2 mv initial squared. Okay, again, cosine of 180 is -1. So I get negative mu nRC times d equals -1/2 mv initial squared. And I can now solve for d. So d is going to equal mv initial squared divided by mu nRC. Oh, and I have a 2 that I dropped there. We could take this further, and it actually might be worthwhile to take further. The fact that the car is not accelerating vertically tells us that nRC has to equal mg. And if I plug that in over here, then my formula becomes v initial squared over 2 mu g, because this m will cancel the m that is in nRC. Okay, so copying that down, 2 mu g. This is the formula for braking distance. And the problem tells us keep everything the same except the fact that you're going faster. So between our two pieces, the factor of 2 will stay the same. The coefficient of friction is going to stay the same. G is going to stay the same. The only thing that's going to change is V initial. So now we need to unravel what this piece means. So the speed increases by 50%. So that tells me that if V1, for example, is 1 meters per second, then when it increases, V2 would be 1.5 meters per second. It increased by 50%. Or, for example, if V1 was 10 meters per second, V2 would be 15 meters per second. And in general, I could write that V2 is 1.5 times V. Oop, that's an I. It should have been a 1. Okay. So the braking distance for our first case is going to be V1 squared over 2 mu g. And our braking distance for when we're going 50% faster, D2, will be 1.5 V1 all over 2 mu g. And I forgot to say it and I forgot to write it, but I thought that square very loudly. Did you hear it? And now if I take the ratio of our new braking distance to our original braking distance, D2 over D1, that's 1.5 V1 squared over 2 mu g divided by V1 squared over 2 mu g. And to pull this out, you have to invert and multiply to get rid of the improper fraction. Everything in the denominator now cancels. The factor of 2 mu g cancels because that again was kept the same. And I'm left with 1.5 V1, the whole thing squared, over V1 squared. Well, the square of 1.5 is 2.25. So in the numerator, I end up with 2.25 V1 squared over V1 squared, which is 2.25 as our answer. Right. So now interpreting. What this tells me is that if my velocity increases by 50%, then the distance I need to brake in order to stop more than doubles. Okay? My velocity increased by 50%, but my braking distance more than doubled. This concludes this part of Unit 10, and it also concludes Unit 10. In Unit 11, we are going to be looking at conservation of energy examples.